Hello and welcome to C++ Weekly. I'm your host, Jason Turner. I am continuing my series on allocators, and this video about C++ allocators was also produced in cooperation with Bloomberg. The views and topics presented in this video are entirely my own. This is continuing where we last left off on allocators, and if you have any interest at all in the game development stuff that I have been doing, I expect that this episode will in fact have direct relevance to games as well. So when we last left off, we had this example right here. We have a vector of PMR strings, a PMR vector of PMR strings. We're using the monotonic buffer resource still at this moment, largely because it gives us an easy way of visualizing what the allocator does. So keep in mind there are other resources and other allocation strategies that are part of the C++ standard library. So we have this PMR vector of PMR strings, and we illustrated that with two short strings here and a long string, we can actually examine this and see that the hello world string, this one right here, that this string and its size, which is decimal 11, are directly encoded in here. And the first 8 bytes were the reference to the allocator that's currently being used. And then I've got hello world 2 and its size of 13 right here. So these things are a little bit awkwardly offset now that they are 40 bytes each instead of 32. And if we come down here, we've got the hello world long string. So we wanted to illustrate what happens when we are using long strings, things that need their own allocation. The short string is just going to fit inside the local object because of the buffer that's built into the standard string object. So I'm using PMR string. If I take the PMR off of this, then what we'll see is the runtime actually has to go out to the heap to allocate this hello world long string, and we don't actually see that being placed in our monotonic buffer resource with our local array that we are dumping. So not a very big surprise here. Exactly as I said, we've got the hello world 2, and we're starting to get to the point where we can just see where these values are stored in the objects. So I actually, that's 13 characters for hello world 2. There we go. All right. So then we've got the next string coming down here, which starts here. And this then 23 should be our length for our hello world long string. And then we've got a pointer at the beginning of this that points to the memory location where this value is actually stored. So what we need to do now is create our own type that can effectively work with an allocator-aware container and pass the allocator information down into its subobjects. So let's go ahead and look at this. I've got this new example here called AA type, and I'm calling it here. These are still our notes from the last episode. And I've added a couple of debugging things here to help us really see what is going on. Let's add a new line here. And I am creating this vector of S's, and I am going to push one back. And I am going to emplace one back. Okay, there we go. And make sure that we are printing out the correct data here. All right, good. So I'm going to create this thing with a string in it. And I'm going to make it a long string so that we can see how it's actually being worked with the allocator. Now we know that this string doesn't know how to work with allocators. Well, it doesn't know how to work with allocators, sorry. It's not type deft to work specifically with the polymorphic memory resource allocator. So let's go ahead and do PMR : string here. And we're doing a pushback, so this thing should have hello long string and emplace back, and this one should also have hello long string. So the emplace back is just calling the constructor that takes 0 parameters. That's all that is doing. And I need to give this an actual object to push back because, well, it's not calling the constructor like ImplaceBack is. So at this point, we're definitely getting good at actually reading these blobs of data coming in here. And I promise that there's going to be some actual fun with this one. So we've got our buffer address start, our item address start, our memory resource. Let's look at this address right here. This is starting at D30 here. Okay. Now, what I have is one with one S object. And we know that this first thing is the location of the memory allocator that it is actually using, because this is the PMR string. And then the next thing is the start of the string data. Now we should, since we're used to looking at these things now, notice that these are heap values. These are way too low to be one of our stack values like we have here. And then we see the length of the string is 17. And so this is pointing into some memory location on the heap. And that means that we have not given vector enough information to know how to forward the current allocator into our struct. So we're going to go ahead and see what that looks like. Now, when we're doing this, we need to give it its special member functions, its constructors most specifically. So let's go ahead and do that. Now, we don't want this to be constructible from an allocator. That would be bad. So we're forwarding this allocator on to the string object when we do this. Now, a couple of things that we have to be aware of. We definitely do have to do the standard move right here to cast this thing to create an R value is basically what we're doing. This is an R value reference. That is an L value. We have to call standard move to create an R value so that can bind to the move constructor of the standard string here. That's an entirely other topic that's quite deep, but we have to do that. Now, what we see here is this code can no longer compile because we are trying to default construct this S object. So let's just go ahead with no parameters. So let's just go ahead and provide explicitly defaulted constructors that don't take any of the allocator values. Now what I'm doing here is saying give me the polymorphic allocator type with no explicit parameters, and then the compiler will automatically default that to whatever is the default template parameter for the polymorphic allocator. That's fine. We want it to do whatever is the default here because this thing may contain containers that are of multiple different types. So we don't want to specify here. If we said this is an allocator of integers, then that would be a problem for us in the future. So I've got the two strings that I'm pushing in here. Neither one of them are short strings. Let's go ahead and take a quick look at this and see what is happening. The first thing that we should note is that these bytes right here are still pointing to some space on the heap, not on the stack. That's weird. And we were expecting it not to. So remember, this is the reference to the current allocator that is in use by this thing. And then this is the memory location, which also looks like a heap address where the data is actually being stored. Everything appeared to compile. It appeared to do what we wanted it to do. So the key thing that is missing here is that we have to notify the Allocator-Aware type, that is the standard vector that is containing these objects, that we are something that can work with allocators, that we have our own allocator type, so the Allocator-Aware container can forward that information to us. And there's a few different ways to do this, but we're going to do it just the most simple way here. The other ways are that we could take a template parameter. Here we could take a templated on the allocator type, or we could specialize one of the standard library template types that say for our type, you know what kind of allocator to get for us. So like I said, we're going to stick with the simplest case here where we just do this using declaration that pulls this type def into our definition, and then therefore standard vector, standard list, all of those things can use our information. Okay, so here we have it. Our memory resource address is 7FFD F0. So that is the memory location where our allocator is living. We come down here and we add one object here, and we'll see this 7FFD2BACBC F0. So that is in fact the address of this allocator. So now we can actually visualize that the allocator has been forwarded in, and that's because we gave the compiler all the information that it needed here by giving this using declaration to the standard library, so vector knows what to do, and it forwards that information on along to us. So now we can see this hello long string coming in, and we know that each of these strings are 40 bytes. So this is the 8, 16, 24, 32, 40 bytes, and then the start of the hello long string. It all worked out good, exactly as we expected it to. So then we come down where we added a second string object, and we see again this hello long string. Now this is after that push back. So that block ends its allocation right around here, and then we should be able to see again, here we go, the address of the allocator. And this is where things really start to get interesting, because the next value that we see is supposed to be the pointer to the memory location where this string is being stored. This is the address of our buffer. Notice this 30 right here. If we take 30 and add 28 hex to it, we get this 58. So that is add 0, add 10, add 20, add 8. So this is now pointing to this location in memory. This hello long string was allocated once. It was given a fixed place in memory. And our string object itself actually moved, though. It moved from here down to here. And we shouldn't be surprised, because of all those examples in the last video, we were showing how memory is never actually freed when we're using this monotonic buffer resource. But what we're actually also starting to see is that we've got this thing pointing into here. And then we can see the start of our next string. The next thing is this address into the start of the memory buffer. Now this is F7DF2BACBDB0. The start of our second location string is at location 98. And if we add 16 to that, then we get B0. And that makes sense because that is 16 bytes after the start of the string. So then what we have is a 0 length string right here. And if you were paying attention, that should be surprising, because we thought that we were in fact initializing it with hello long string. But part of the problem we just ran into is when we are doing this default initialization that takes an allocator, not the copy constructor, not the move constructor. When we call this one, we are not giving it any default value. All we're passing to it is the allocator. So this in-class initialization gets overlooked. So this is something that you're going to have to keep in mind with all these extra constructors that you're creating. So making sure that you are allocating the values that you think that you are allocating. So now we should see in our memory the first one, which is default constructed, which is hello long string, and then the one that is in placed back, calling the constructor quote with 0 parameters, but it's actually calling the constructor that takes an allocator, should say hello from the PMR constructor. Hello long string here, vector body again in here, and then we've got the next string allocated here, and then we've got the hello from the PMR constructor down here. So we're starting to see this interleaving of memory where this thing is now the vector, which is containing an element which is pointing up here, which is containing an element which is pointing down here. And we're starting to see memory fragmentation occur. So that's just something that you need to be aware of, that even with custom allocation strategies, it's possible to get this kind of fragmentation of memory. So these are all just things to be aware of, that custom allocators, they aren't magic. You still have to think about what you're doing. And if you're going to this level of optimizing your code with custom allocators, you really need to be aware of these things. And just a reminder again that we are using the most simple custom allocator. This is not thread safe, and there are others in the standard library, and we might get to those in a future episode. But I do expect to start putting these principles to work in the game projects that I've been working on. So getting this stuff right can be hard, actually. I noticed that in the standard function in the C++ standard library, if you go and look at the constructors on cppreference.com here, then we can actually see that the constructors that take a custom allocator have been removed in C++ 17. And it turns out this came from this Jonathan Wakely paper from 2016, where they say, the semantics are unclear of these constructors that take allocators. There are technical issues with storing an allocator of a type-erased context and recovering that allocator for later allocations, and so these constructors should be removed. So getting this right all the time can be hard. So we know that all of the C++ standard containers are allocator aware and can work with R types that are enabled for custom allocators. The question is then, which other types in the standard library allocator aware? We know that standard function no longer is, or at least it can't work with allocators. So we have standard tuple, which can take an allocator with its various constructors, and the first parameter in this case is this placeholder parameter type that's std allocator argt, so that during overload resolution it knows which constructor to call, because otherwise it has all of these constructors that have variadic template arguments, and it would be difficult to distinguish which constructor you are intentionally trying to call. But we don't have support specifically an optional or variant. I've seen papers that discuss doing this. So you're maybe not necessarily always going to get the support that you want from the standard library with automatically forwarding the allocators into your types, but that is something that you can do in your own code. So we know that we need to pay attention to how and if our memory is growing. We need to choose the correct allocator for our use case. We haven't really dug into the different options there. Make sure we properly nest our allocator aware types. We figured that part out. Understand which standard types are allocator aware. When building custom types that support allocators, make sure to initialize all the subobjects correctly. We are calling new constructors, creating new constructors, and we have to pass these allocators along to all of them, and it's possible that we'll mess up our default values. That's a really important one. We need to notify the allocator-aware containers that we're using that we support our own allocators being passed to us. So let's take one more look at this here. We need to come back to this. This is all a little overcomplicated because these polymorphic allocator is copyable, and we can just do this. And now the next thing that we need to know is that the polymorphic allocator does in fact have a default constructor, and when it is default constructed, it uses the get default resource as the underlying memory resource. So while technically this code does work, it does have a few problems. We've got some mismatched initializations that you can see here. When I have my default construction, I've got hello long string. When I'm calling the allocator-aware constructor, default constructor, then I'm initializing this hello from the PMR constructor. And that was helpful for the sake of debugging this code and trying to get an understanding of what it does. This is not at all helpful for what we would want in the real world. Furthermore, this code is missing the rule of 5, and it is missing its allocator-aware copy constructor. So we can go ahead and fix those problems relatively easily with a little bit of delegating constructor help, and let's do it. So for this copy constructor, we never want to copy the allocator from the string that was passed to us from the other struct. So we want to initialize our own allocator and always pass that in so we can use this default initialized one. And this becomes our constructor that is both allocator aware and our normal copy constructor. We actually get to leave the move constructor as explicitly defaulted because in this case, we just want to do whatever the contained allocator aware types would naturally do. And I'll group these two move constructors down here together. And this is correct for our allocator aware move constructor. We want to move the other object that is coming in and then take whatever allocator is passed to us. So for the sake of grouping, we've got our two default constructors, our copy constructor that acts as both of the required copy constructors, our explicitly defaulted move constructor that's going to do whatever the other types inside this class would naturally do, and our move constructor that is allocator aware, and it takes an allocator for it to use for the allocation of the new string object. So now to go ahead and wrap this up with sticking with the rule of 5, we need to be explicit about our assignment operations and our destructor. So if you've watched my videos on avoiding code bloat and where no except matters and that kind of thing, by explicitly defaulting this move constructor and this destructor, if they could be trivial, they would be trivial. If they can't be trivial, they won't be trivial. In this case, we know that they can't be trivial. If they could be no except or const expr, then they will be those things by default, and that is true also with these assignment operators. So the only thing missing now is that it turns out that it's actually quite handy to have a get allocator helper function here that lets you get the underlying allocator. Now, with the way that these PMR allocators work, getting these things by copy, as we've seen already throughout this code, is a pretty natural thing to do because all they are is a reference to the actual underlying polymorphic allocator itself. So let's just go ahead and return a copy of the one that our string object happens to be containing for us because standard string has this already. So there we go. This wraps up the minimal example that is correct, that has all of the things that an allocator aware type needs to have. So hopefully this episode was useful and educational, and this is the kind of thing that you will be able to apply in your own code base as you're making your own allocator aware types that you are using specifically with the PMR containers. Really, in this case, this is very polymorphic allocator specific. We're relying on the behavior of what the polymorphic allocator does while still being fully supporting the allocator aware types in the standard library. I will again be sure to have this example available for you to look at in the notes for this video. So thanks for watching this episode of C++ Weekly.